So in the last video we talked about a lot of vocabulary related to linear differential equations, and what we're really going to be focusing on are a very specific kind of problem, linear differential equations with constant coefficients. So that's the equations that look like this. Here n is the order, so the nth derivative is the highest term that we see. And then it's just a bunch of terms, one term for each of y, y prime, y second derivative, third derivative, and so on. They don't all have to be present. Some of these coefficients could be 0 and those terms are gone. But the point is that the highest we see is the nth derivative, so that tells me it's the order of the equation. It also tells us how many independent solutions we're going to have to find to solve such a problem in order to construct the general solution. And last time we talked about how in chapters 9 and 10 we'll learn actually a very simple way of identifying a solution to what's called the homogeneous equation. If the right-hand side of the equation is just the zero function, there's a very easy way to solve these problems and identify all n independent solutions so that the general solution of this homogeneous problem is just a linear combination of those functions that we will find. So the constants here can be anything, and that freedom to put any constant as these coefficients on this solution to the homogeneous equation is what allows us to solve initial value problems later. And then in chapter 11 we're going to look at one particular way of finding just one solution to the general equation that we're trying to solve. And then all we do is we add that linear combination that solves the homogeneous problem, and we add that to the particular solution to the general problem. And linearity of the problem takes care of the rest for us. This function will be a solution to the equation, but it will also give us a general format with n unknown constants, which we can then determine by initial conditions. So this is what we talk about, the uniqueness of initial and boundary value problems. When we did first order equations, there was only one constant. We only needed one condition to determine what that constant was. Now if we want to do a second order problem, we need two conditions. Third, we need three, and so on. We'll see this a little bit more with some examples why that is, but that is the case. So this particular, how I've written this here, this is called an initial value problem, because all the conditions that we're given have to do with an initial input value of 0. It doesn't have to be 0, but typically problems that are related to time-related functions, 0 is the initial time. So in this case we're just going to be given a bunch of values. We know that the function's value at 0 is some number z0. We know that the first derivative's value at 0 is some number z1, and so on and so on. And we have to go up to the n minus first derivative because that'll give us the nth condition. So we're given these information. Typically these pieces of information come from the quantity that we're modeling. We want it to have certain properties related to this, or these are observed properties. We observe a phenomenon occurring at a certain time and we take a bunch of observations, and then we understand the basic idea of the model, which is the equation itself. And then if we solve the equation and then force the particular exact solution to fit the observed conditions, then we have a function which we can now use to predict the future, for example. How is this quantity going to behave at later times? And we're listing this as x as our independent variable, but it could be very well be t for time. So the point is, once you have your general solution, which we'll, again, that's what we're going to be doing the rest of the course, is finding this general solution. Then all we do is we plug this function y into all of these equations. So we have to differentiate it and then plug in 0 or whatever value it is. It doesn't have to be 0, it could be other values. And many of these conditions could actually be, you could have n conditions all about y itself. You could have y of 0 is 5, y of 10 is 3, y of 25 is 7. The point is, they don't have to be of this specific form, but if they are of this specific form, it's called an initial value problem. The point is, because we have n independent solutions from our homogeneous part of the problem, when we plug y into these initial conditions, the numerical equations we get are going to be n equations with n unknowns, and they will be independent equations, which means there will be a unique solution. There will be a unique set of numbers, C1, C2, and so on, that will give us the specific solution y to this specific initial or boundary value problem. So we just have to solve systems of equations, which you can do in Wolfram Alpha, for example, using technology very easily. I don't need to see step-by-step procedures of solving systems of numerical equations. That's not an important thing. This isn't algebra class. You just need to find those constants. So again, just kind of want to make another note about linearity here as well. We talked about that in the last video, but let's kind of understand what that really means again. So, as we saw, if we have this first example here, it fits the form of a linear equation. It's a second order equation. It's linear because I have three terms on the left, one for the second derivative, one for the first derivative, one for the function itself, and they're all raised to the first power. So that's what makes it a linear equation. So in our general format, x is being multiplied by the first derivative, so that's our a1 of x, functional coefficient is x. Y only has a 1, so, well, a0 of x happens to be a constant. That's okay. So some or all can be constants, but if they are all constants, we call it a problem with constant coefficients. So this is a second order linear equation with, and that's all we can say. The next example is nonlinear because we can see that the term where y appears, y is squared. So that's nonlinear. And then in the third example, y prime and y both appear to the first power, but they're multiplied together, which creates a nonlinear term. All right, so those are basically the things you look at are all the appearances of y in my equation, do they all appear once per term and to the first power? Yeah, the derivatives, there may be derivatives, but that's fine. But each occurrence of the symbol y occurs once in each term on the left side of the equation, and it's raised to the first power.